Okay, good morning, everyone. Day 4. We'll begin the process of division of polynomials. Yesterday we looked at adding, subtracting, and multiplying polynomials. Today we'll begin the process of division of polynomials. It's a little more involved, so I'm going to break this up into 2 lessons, day 4 and day 5. Before we actually get into division of polynomials, let's lay some foundational knowledge here. We need to go back in time, way back into 4th and 5th grade maybe, or even 6th grade. Okay, and we need to remember the process of long division. So let's take a look at the process of long division. Step 1, when you do long division, you divide. So here we're taking 74 and we want to divide it by 3. And so we ask ourselves, how many groups of 3 go into 7? How many groups of 3? Well, there are 2 groups of 3 that go into 7. So we take 2 times 3 and we get 6, and then we put that underneath the 7. We put that underneath the 7, and we put the 2 groups of 3 above the 7. All right? And so now we subtract 6 from 7. So now we subtract 6 from 7. So we did step 1, step 2, and then step 3, subtract. So 7 minus 6 is 1. In step 4, now we bring down the next number. So we bring down that 4. And then we kind of repeat the process again. We say, how many groups of 3 go into 14? Well, there are 4 groups of 3 that go into 14. And so we put that 4 above the 4. And then we go 4 times 3 is 12. We go 4 times 3 is 12. And then we subtract. 14 minus 12 is 2. Okay. Now, we have no more numbers to bring down. And our remainder is now less than our divisor. So we are done. Okay, so we have a remainder of 2. Okay, one good check is we can, and I like this, and we're going to use this so much tomorrow, but check your answers. The dividend, they didn't actually, the dividend, the number underneath here, the dividend, the number underneath there, that should equal the divisor times a quotient plus the remainder. Well, that's a different example, so let's just check using the dividend. My dividend here was 74. 74. Okay, and then my divisor was 3. My quotient was 24, and my remainder was 2. So 3 times 24, what is that? 72 plus 2, 74. Okay, so that's one way. I'm sure you were never taught to check your answer that way. I kind of remembered way back. Of course, that was almost 45 years ago. Okay, I kind of remember that, though. Okay, so that's one way you can check. So let's take a look at the dividend form, which is going to be really, really important for us tomorrow. Okay, I always like division along polynomials because it's like you go way back in time. Way back in time. And everything's almost the same. The process is the same, except only one difference. Back in 4th and 5th grade, we were working with numbers. Now we'll be working with polynomials. Okay, makes it a little more difficult, but the process is the same. So let's say here we have 75 as the dividend. It's the number underneath the box, and the divisor is 4. Okay, so we say how many groups of 4 go into 7? Well, there's 1 group of 4 that goes into 7. And then we go 1 times 4 is 4, and we put that underneath the 7. And then we go 7 minus 4 is 3. We bring down our 5. And then we ask ourselves, how many groups of 4 go into 35? Well, there are 8 groups of 4. So we put the 8 above the 5. We go 8 times 4 is 32. Rewrite that underneath the 35, and then we subtract. Okay, and we get 3. There are no more numbers to bring down. I see that my remainder is 3. My remainder is 3. And so, okay, I am done. So as a check, if I take my dividend, which is 75, and I'm set that equal to my divisor times my quotient plus 3, I should get 75, and I'm sure I do. 4 times 18. So 4 times 18, that's 2. That's 72 plus 3. And that's 75. Boy, that's almost just like the problem above, right? So what was the difference here? So we had 75. Were we dividing? Yep, it was 75 divided by 3. This is, oh, that one was 74. Okay, interesting. All right. So let's look at one where we don't have a remainder. So if I have like 188 and I divide that by 2. So 2 goes into 18 9 times, and 9 times 2 is 18, and I subtract and I get 0, and I bring down my 8. Don't need that 0 in front. And then 2 goes into 8 4 times, and 4 times 2 is 8, and I subtract, I get 0. There's no other number to bring down. Okay, my remainder is 0. Okay, using the dividend form, I can say that 188 is equal to my divisor, which is 2 times my quotient 94, and with a remainder of 0, no remainder. Okay, so that, again, the dividend form is going to be really, really important for us tomorrow, except we'll be working with polynomials. All right, so now with that background knowledge, we can kind of begin the process of long division of polynomials. I want you, just before we get there, though, I want you to, as a practice, pause the video and try these 3 problems. I want you to write the dividend form. The dividend form of those 3. If you take 822 divided by 7, what is the dividend form? Number 2, if you take 731 and divide it by 5, what is the dividend form? And then number 3, if you take 762 and divide it by 3, what is the dividend form? Okay, good practice. We're gonna turn it up a notch tomorrow. Okay. Now let's review factoring and finding the zeros. The zeros we also call the roots or the x-intercepts. The x-intercepts is where the graph crosses the x-axis. The zeros, right? The zeros, x-intercepts. Stuff we learned last trimester of polynomials. So we're going to review factoring and finding the zeros of polynomials. Quadratics. Recall that if a number is divided by any of its factors, the remainder is 0. Well, I just did an example like that. I took a number, 188, and I divided it by 2. I got 94, remainder is 0. So 2 is a factor of 188. 4 certainly wasn't a factor of 75 because I got a remainder of 3. 4 wasn't a factor of 75, and neither was 3 a factor of 74 because I got a remainder. But 2 certainly was a factor of 188. I got a remainder of 0. Okay, very important. So recall that if a number is divided by any of its factors, the remainder is 0. Likewise, if a polynomial is divided by any of its factors, the remainder is 0. Well, that just makes sense. The remainder theorem states the big concept, the number 1 concept in this entire chapter, the remainder theorem, states this. And then that also means the factor theorem too. The remainder theorem states that if we take a polynomial is divided by a factor, a potential factor, x minus a, the remainder is the value of the function at x at a. So if x minus a is a factor of the polynomial p of x, then p of a is equal to 0. I know it says a lot, okay? But we're going to walk through this. But this is the most important remainder theorem and a factor theorem. They kind of say the same thing. The most important theorem concept in the entire chapter. So let's look at this in detail. For any polynomial p of x, x minus a is a factor of p of x if and only if p of a is equal to 0. So let's say here I have a polynomial. They give us x squared minus 1. Let's factor that. We should be able to factor that. That's a difference of squares. X squared minus 1, I can factor x plus 1 times x minus 1. Let's find a 0 and set that equal to 0. If I find the zeros of that polynomial, I'll get negative 1 and 1. Okay, it's easy to see because I've just verified, I just factored x squared minus 1. It's easy to see that x plus 1 and x minus 1 is a factor of that polynomial. Well, my 0 for x minus 1 is 1. So all the theorem says is this: hey, if I take that 0 and I substitute it into that polynomial, and if I get 0, that meant the factor for that 0 was a factor of the polynomial, okay? All right, so that's what they said, because p of 1 is equal to 1 squared minus 1 equals 0, x minus 1 is a factor of x squared minus 1. Well, we knew that because I just factored x squared minus 1. Okay, so we knew that x minus 1 was a factor of x squared minus 1. But here we just took the 0, which is 1. The 0 is 1 for the factor x minus 1, and we plugged it into p of x, and we got 0. Okay, and that's what the theorem says. So let's just take a look at some examples here. Is x minus 4 a factor of p of x is equal to 3x squared minus 11x minus 4? Well, let's see here. If x minus 4, we have to check. X minus 4 is a factor. The 0 for x minus 4 would be this. X minus 4 is equal to 0, x is equal to 4. So now let's take that 4 and let's plug it into that polynomial and see if we get 0. If we get 0, then that means that x minus 4 is a factor of 3x squared minus 11x minus 4. When I substitute in 4 into that polynomial, I get 0. So x minus 4 is a factor of p of x. That is true. X minus 4 is a factor of p of x. I found the 0 for x minus 4, that was 4. I plugged it into the polynomial p of x, I got 0. Okay, so x minus 4 is a factor of p of x. Let's look at the next example. Is x plus 2 a factor of that same polynomial 3x squared minus 11x minus 4? So I start with my potential factor. It may not be a factor. We don't know. It could be it's a potential factor. We knew that x minus 4 was a factor because when we got the 0 for x minus 4 and we plugged it into the polynomial, we got 0. But is x plus 2 a factor? Well, let's see here. So we have to find a 0 for x plus 2. So the 0 for x plus 2 is x is equal to negative 2. So now we'll plug in negative 2 into that polynomial, and we get 30. We don't get 0. So x plus 2 is not a factor of that polynomial 3x squared minus 11x minus 4. It is not. And then let's try one more. Is 3x plus 1 a factor of that polynomial? 3x plus 1. Again, so we start with our factor 3x plus 1. We find a 0. 3x plus 1 is equal to 0. 3x equals negative 1. X equals negative 1/3. Now we plug in negative 1/3 into our polynomial. So we have 3 times negative 1/3 squared minus 11 times negative 1/3 minus 4. And voila, we get 0. So that means that 3x plus 1 is a factor of that polynomial. So what were my factors then? Well, one factor was 3x plus 1. Well, I tell you what, here's my polynomial, 3x squared minus 11x minus 4. Let's factor that, okay? Let's find the zeros. Okay, so here, if I factor that, I'll get 3x plus 1 times x minus 4. Okay, 3x times x is 3x squared. 3x times negative 4 is negative 12x, plus 1x gives me negative 11x, and 1 times negative 4 gives me negative 4. Okay, so factors. My zeros then would be x is equal to negative 1/3, and x is equal to 4. So we found that 3x plus 1 was a factor of that polynomial, and we found that x minus 4 was a factor of that polynomial. So all the theorem really says is this here, okay? If we take a factor and then we evaluate a 0 and we plug it into the polynomial, we should get 0. In other words, we have found the x-intercepts. We have found the zeros. So this was my polynomial then, p of x. This was equal to 3x squared minus 11x minus 4. So that was my polynomial you see right there. And again, using Desmos and looking at this, I can see that each block is 2, so I can see that 1, 0 is x is equal to 4 and y is 0. So that's my x-intercept. X is equal to 4 and y is 0. And then the other 0 was negative 1/3 and 0. Okay, and all the theorem really says this. Okay, so if my 0 was 4, then my factor was x minus 4, right? And if my 0 was negative 1/3, x was equal to negative 1/3. Multiply by 3, 3x equals negative 1, and 1, 3x plus 1. So the other 0 would have been 3x plus 1. Okay, and all the theorem really says that, hey, if x minus 4 is a 0, is a factor of that polynomial, if you take it 0, which is 4, and you plug it into p of x, and p of x is y, right? You should get y is equal to 0. Well, by golly, that just makes sense because that's the x-intercepts is where the graph crosses the y-axis. That's where y is equal to 0. Okay, and that's all the theorem says. Take the potential factor, find a 0. Plug that 0 into the polynomial equation to see if you get 0. If you get 0, that means that that potential factor, is a factor of the polynomial. If you don't, then it's not. Okay. All right, so what I want you to do, using the factor theorem, verify if x is x minus 2 a factor of 5x squared plus 14x minus 3. Is x plus 3 a factor of 5x squared plus 14x minus 3? Again, find the zeros for x minus 2. Take that 0, plug it into 5x squared plus 14x minus 3. If you get 0, then x minus 2 is a factor. If you don't, then it's not. And ditto, take x plus 3. Find a 0 for x plus 3. Okay, plug that 0 into the factor, 5x squared plus 14x minus 3. If you get 0, then x plus 3 is a factor. If you don't, it is not. All right, and then I want you to do the same thing for x plus 1. Is x plus 1 a factor of x cubed plus x squared minus 4x minus 4? And is x minus 4 a factor of that same polynomial, x cubed plus x squared minus 4x minus 4? That is a cubic polynomial, but this is where we're going. Okay, so this is the beginning. Tomorrow we'll actually look at division of long polynomials, but we'll incorporate today's lesson into tomorrow's lesson. I did not want to give you the entire lesson in one day. I think it's too much